Hey, back for another round of astronomy, and we'll just keep going. We're talking about Hubble's law, Hubble distances, Hubble constant, and we're just going to continue that today. Last time I left you, we were discussing both the age of the universe and the size of the universe. So I thought we'll start off with a quote today. One of the most basic yet powerful principles of physics is that there exists a universal speed limit, 186,282 miles per second. That's 299,792 kilometers per second, which not even light can break. For most of human history, the speed of light played little to no importance in our lives. But as we developed and improved our telescopes to peer deeper and deeper into the heavens, we became acutely aware that astronomical speed limit of light is challenged by astronomical distances of space. And that's what we're going to hone in on today. The speed of light is challenged by astronomical distances of space. Okay, so to summarize, remember we have used Hubble's law, first and foremost, to gauge distances to objects. We find the redshift of a galaxy, we use the Doppler effect to get the speed of that galaxy, and then we apply Hubble's law to find the distance to that object. Okay. So that's the first thing that we can use Hubble's law for. Now we're going to get into some more of the exciting consequences of Hubble's law, things that go beyond just measuring the distance to galaxies. And I would say that this is the gateway into a field of astronomy and/or physics called cosmology, the study of the universe. We can kind of see where that already comes in, the lifetime of the universe, the size of the universe, but we're going to go further in terms of studying the universe itself. So we've got the distance to objects and the age of the universe. Now here's something that's interesting, and we're going to spend most of our time in lecture today on this, is the size of the universe. You say, well, what do you mean? We already have that. I say, we have found a size of a universe. But in some sense, there's two. And of course, Hubble's law gives us an evidence that the universe is expanding. And that is really important if we rewind the clock. Here's an example. If galaxies are moving away from us today, by and large, that means that yesterday they were closer to us, which means 2 days ago, they were even closer to us. And 10 years ago, those galaxies were closer. And 100 years ago, they were even closer still. Well, why stop there? Let's go 1,000,000 years back and they were closer, or 1,000,000,000 years back, they're even closer to us. And you can see where this is going. If I rewind that clock, if I just take that, if I say they're further away from us today than they were yesterday, I take that idea and I rewind it back all the way 13 billion years backwards, I end up at a point in time where all the galaxies, all the material that forms those galaxies is all in the same location. Well, okay. So sometime in the distant past, all that material was on top of each other, and then something must have happened to cause that material to start moving outwards. So that's what we refer to as, and you already know it, the Big Bang. The Big Bang is a consequence of taking Hubble's law and running it backwards in time. So we can take the current observations in our current model and we extrapolate it backwards into time. Now there's some other observational evidence for the Big Bang. We'll get into that as well. But I just wanted to highlight that Hubble's law tells us something about that as well. Okay, so the question that we want to answer today, how far can we see? How far is it actually possible to see in this expanding universe? And I like to think of it as a treadmill. Say the treadmill's going at 10 miles an hour and you're only running at 5. You've seen what happens on this. I just pulled this clip up.
Look at
right?
this. This is one of the weirdest things we've ever filmed. Look at this.
This is
What
mental.
a sight
What
this is. Alright, there goes the first milk.
Oh, it's all over
That's
from this
tipped
point.
the tray off balance. Oh, there goes the rest of it.
No.
Oh,
Slow-mo.
Oh, God. My legs are just gone.
completely Supermaned it. You're midair, falling, belly flopping towards a moving floor.
Oh, God. You can see all the milk shooting out the end of it.
Boom.
That's the-
Oh.
Oh.
Your foot skimmed the surface and didn't touch. We're like treading milk for a second, like without touching it. There's the waiter as he goes down. Oh, hefty impact.
Is that the tray coming down after me?
That's the tray, yeah. Alright, let's
Okay. So that's the idea. You know that if you're running too fast on a treadmill, you'll move forward on the treadmill. If you run too slow, you'll move backwards. Okay? And of course, the idea is there's that nice, just right, where you're running at exactly the same speed as the treadmill is. And you go. Now here's the idea. Here's that's the analogy. Okay. Now let's take it into our astronomy. Pretend for a moment that the treadmill represents space. Universe, the space in our universe. Okay. That space is expanding, so that represents the treadmill. It's moving, if you will. Now the next thing, the waiter. Instead of thinking of it as a person on the treadmill, let's think of it as light. Light is trying to run through space. Okay. Now, if space is stretching slower than the speed of light, then light can move forward through that space. But what happens if space stretches faster than the speed of light? Well, if that space is stretching faster, that means that light can't keep up on that treadmill. As space stretches, light will fall further and further behind, much like the waiter who can't keep up running on the treadmill. Light will fall backwards. And of course, there's that Goldilocks, that perfect line, that perfect distance, where the stretching of space exactly matches the speed of light. Okay. That represents what we call the cosmic event horizon. Or some people will call it the Hubble distance. Okay. So Hubble's law tells us as you move further and further away from Earth, for example, the distance, the space between us and that point in space is expanding. And Hubble's law tells us how quickly it expands. The Hubble distance, the cosmic event horizon, is how far away you have to be from Earth for the stretching of space to exactly match the speed of light. We actually already found that. That's that 13.6 billion light years. So now I have a question for you. Okay. Let's assume today a galaxy is observed to be on the cosmic event horizon. It is just as far as it can be. Okay. The next question for you. Tomorrow, will you actually be able to observe that galaxy? Go ahead, take a minute, come up with an answer. You got it? Good. So remember that let's say that galaxy is on the cosmic event horizon. That means tomorrow it will be further away, right? Don't forget that galaxy is moving away from us. So tomorrow, if today it's on the cosmic event horizon, that means tomorrow it will be past that cosmic event horizon. which means that light emitted from that galaxy tomorrow, will it ever be able to reach us? No, right? Tomorrow, it's beyond the cosmic event horizon. Let's say it emits some light. That light is traveling through space, but because it's beyond the cosmic event horizon, that space is expanding faster than the speed of light. So light is now running on a treadmill that's too fast. It will never reach us. I kind of think of it like this. You have objects, so there's a circle centered on Earth, a sphere, if you will, centered on Earth. The radius of that sphere is 13.6 billion light years. And the boundary of that sphere represents the cosmic event horizon. If you cross the cosmic event horizon and emit some light, we will never be able to receive that light. And of course, as time goes on, the universe keeps expanding, whereas our cosmic event horizon stays the same. What does this mean? That means more objects will continually cross the cosmic event horizon. We can see them today, but tomorrow, when they cross, we'll no longer be able to see them. So, in some sense, you could say we have two universes. We have objects that are inside the cosmic event horizon, what I will refer to as the observable universe. These are objects that if they emit light today, we can receive that light sometime in the future. Maybe it's 2.5 million years in the future, or maybe it's 3 billion years in the future. But at some point, we'll be able to see those objects. But then there are other objects which used to be in our observable universe, but as time progresses, they have passed outside the cosmic event horizon. So I would say that we can receive light from them since they were inside the cosmic event horizon. And so we know they exist. But since then, they have passed outside the cosmic event horizon. So sometime in the future, we'll no longer be able to observe them. Physically speaking, right? Now run forward in time. If the universe is expanding, but our cosmic event horizon stays the same distance, more and more objects are going to pass out of our observable universe. It's kind of sad, really. Right? Objects, galaxies will continue to cross that cosmic event horizon. And so sometime in the distant, distant future, we'll no longer be able to see those galaxies. You say, is there an edge to the physical universe? Yes. Yes, there is. And we call that boundary the particle horizon. So the particle horizon is the boundary of the physical universe. So anything inside the particle event horizon is any object that emitted light at any point during the history of the universe that we could actually receive. The physical universe is closer to 46 billion. You can almost get there. Say you have this galaxy that we're talking about again, right on the boundary. So it emits light. It takes 13 billion years for that light to reach us. A conservative estimate would be that the time that that light reaches us, 13.6 billion years in the future, the galaxy has moved, conservatively speaking, another 13.6 billion light years away from us. So right away, we know that, okay, that galaxy that we've talked about in our question, When we receive light from it, it is 26 billion light years away, right? As light traveled the 13 billion light years, this galaxy moved another 13 billion light years away from us. So a conservative estimate would be that the physical universe is at least 26 billion light years in size. It's actually closer to 40. You might also notice, I've been talking about the observable universe centered on the Earth. But what happens if we're not in the Milky Way galaxy, but rather we're in the Andromeda galaxy? Do they have the same observable universe as ourselves? No. Remember, the observable universe is dictated by how fast the speed of light moves, and it's centered on the Earth. Let's say for a moment we're sitting in the Andromeda galaxy over here. Okay? The Andromeda galaxy is offset by about 2.5 million light years, okay? Which means the observable universe for the Andromeda galaxy, it mostly overlaps with our own, but there's a part of the physical universe that the Andromeda galaxy will be able to see that we will not. But conversely, there's a part of the observable universe that we can see that people in Andromeda galaxy wouldn't be able to. Assuming intelligent life and all. Okay. Not going to go there. Okay. The question I have is, what do we see? Okay. Remember, the opening slide was just the infographic. Excuse me. The opening slide was just the infographic about building better telescopes to see further back in time. Further back in time means that we're seeing closer and closer to that cosmic event horizon. And the question is, what can we see? What will we see if we get all the way to that cosmic event horizon? And this is where predictions start matching our models. I said Hubble's law, if we extrapolate it backwards in time, would say that all of the material that comprises our universe at one point started out at the same location. If everything were located at a single point, all the energy were located at a single point, then the temperatures would be astronomically huge. There's a prediction that can be made there because of that. And here it is. If temperatures are really high, then at some point at the very beginning of our universe, you had protons and electrons that were not incorporated. Okay? You have your protons flying around, you have your electrons flying around. Okay? This is a plasma. There's actually something that begins earlier than the plasma, but we'll start with the plasma. Okay? So protons and electrons are swimming around freely. Okay? Now, as the universe expands, okay, the temperature goes down, right? You could think of it, I guess, as you use some of that energy to expand the universe itself, the temperature must go down. And eventually, the temperature goes down low enough that your protons are moving around really quickly. Your electrons are moving around really quickly. They slow down enough that they begin to combine and form hydrogen. Now, remember, if an electron goes from the top ladder rung and drops down to the lowest ladder rung, it must emit light. So what this process is sometimes referred to as the recombination period. It is the point in the distant past where the universe has sufficiently expanded so that the temperature has sufficiently dropped so that protons can actually capture an electron. During that capture process, when they proton and the electron combine, they emit some light. And that light begins to travel through space. Now, if space is stretching, what happens to the wavelength of that light as it travels through space, which is stretching? Go ahead. What do you think happens? The wavelength gets stretched. Based on our ideas about how space has stretched, Hubble's law, we can estimate what the wavelength should be today. If we know what wavelength of light we should measure. It's in microwave regime. So here's the prediction now. There should be microwaves coming from space that we can measure that are from this recombination period. That's the prediction. Hubble's law, 1920. We go fast forward now. We actually have to go to 1965, Bell Labs. And at the time, and I'd have to look up the particular researchers' names, but at the time, they were measuring microwaves. And there was something funny. Shoot, what were they trying to do? I think they were trying to measure something like microwaves from the sun, or maybe it was the upper atmosphere. I can't remember exactly, but they were interested in microwaves. Okay? And they had this buggerish problem. Okay? No matter which direction they pointed their microwave telescope, and I know this doesn't look like a telescope, but it's a telescope for collecting microwaves. That's why it looks different. Okay? No matter where they pointed their microwave telescope, they always had this annoying background signal. Okay? And we're talking about so annoying that what they did was they went through and of course, they made sure the electronics were right and to make sure that they tested their measuring equipment. They went so far as to actually enter inside this horn. Okay, this is what actually collects the microwaves. The equipment's over here. So they actually had to go inside the horn. They cleaned out bird poop and birds' nests and everything. No matter what they did, they could not figure out what this background signal was. Okay? They wanted to get rid of it because it was gumming up their measurements. Little did they know that down the road in Princeton, this idea was being developed about the fact that we should be able to see microwave light from the combination period of the universe's formation. So you have two separate ideas going on. And then one day, I can't remember, serendipitously, these researchers were talking about this annoying microwave background signal. And somebody said, well, you know, these guys at Princeton have been working on this microwave background signal from the early universe. You should go and talk to them. And so it happens, the cosmic microwave background. The theory, the prediction was being developed at the same time that a separate group happened to be doing the measurements. Now, it was serendipitous, right? These guys were not looking for a cosmic microwave background. They were trying to do something else and kind of stumbled upon it. So that's one observation that is, or one prediction that has been observed. Gives us some confidence. It actually turns out as well that this is a black body. You can think of the hot, dense, early universe as being a black body. And so we can measure the black body spectra of the cosmic microwave background. And it has the characteristic black body shape and the peak right here. So we can apply Wien's law to this black body spectra. You'll get a temperature, if I recall correctly, of about 2 Kelvin. Of course, the other cool thing is that if you have the temperature today and you know how much the wavelength has been shifted, we can find the temperature in the distant past. If I know the peak wavelength today, and I know how much that peak wavelength has been shifted by, I can find out what the peak wavelength was in the distant past, which means I can find what the temperature was. So let me show you the oldest picture of the universe. I know it's not much to look at. So what this is, now of course this, it's not using this microwave telescope, but we now have telescopes in space and on the ground that collect microwaves. Okay? I think the most recent one is something called Planck telescope. So it's not a visible light, it's not infrared, it's microwave telescope. And this is what came from the Planck's telescope. Okay? And as I hinted at, the red spots are falsely colored to indicate regions of space, regions of the early universe that are slightly warmer. The blue regions are regions of space that are slightly colder. And the difference in temperature between the reddest of red and the bluest of blue is about, now we have to tenths, hundredths, thousandths, about 10,000ths of a Kelvin. So these are really, really tiny differences in temperature. The important point to note is that those differences in temperature, we think, are why galaxies, stars, planets even exist. One material, this hot plasma, if you have one material and it's at slightly different temperatures, the hotter regions will be less dense. The colder regions will be more dense. Next question for you. In which region would you expect stars to more easily form? You say, well, stars form from a cloud of gas. So you are more likely to have star formation in regions that are more dense. More dense, more material, more likely to form stars. So this difference in temperature indicates a small difference in density. And so that small difference in density would indicate that you would have more stuff forming in the blue regions than the red regions. So there's a new prediction. A new prediction. We should see regions of space that have more material. We should see regions of space that have less material. Hang on to that idea. Okay? This is why I said we're going to get into the structure of the universe. We're going to start talking about how the universe is actually organized. Hey, thanks for your attention. I'll see you next time.